All right, let's get right into it. Today, we're going to be looking at this really groundbreaking paper by Brendan Lake and his colleagues that tackles a huge question about the future of artificial intelligence. It's titled, Building Machines That Learn and Think Like People. And this really gets to the heart of the matter, doesn't it? I mean, we're constantly hearing about how AI is getting smarter, more powerful, more capable every single day. But the big question is it really thinking? Thinking like a person does. And look, let's be clear, there's absolutely no denying that modern AI, we're talking deep neural networks here, has made some just incredible leaps. Honestly, the progress in the last decade alone is, well, it's been mind-blowing. It's doing stuff we thought was still decades away. And you see this stuff all over the place, right? AIs can pick out objects in your photos, they can understand what you're saying to your phone, they can master these incredibly complex video games. They can even beat world champions at games like Go. They are, simply put, amazing at recognizing patterns. But, and this is a big but. So, take a look at this number, 924. What is that? That's the number of hours a top-of-the-line AI needed just to get good at the old Atari game Frostbite. Think about that, 924 hours. That's over a month of nonstop playing. And right there, that starts to hint at a massive difference between how they learn and how we learn. And that crazy number, that 924 hours, it really highlights what the paper calls the learning gap. It's not just about whether the AI can win the game, it's about the completely different and frankly inefficient way it gets there. So yeah, let's stick with this Frostbite example. The whole point of the game is to build an igloo by hopping across these moving ice floes. Sounds simple enough, doesn't it? But it turns out to be a perfect way to show this massive learning gap in action. Okay, just look at this comparison. It's kind of staggering. The AI, it trains for 924 hours and still can't even get to 10% of what a pro human player scores. A person, we figure out the basics in, a few minutes? And we can get to an expert level in maybe a couple of hours. But here's the real kicker. We can invent new goals on the fly. We could decide to try and get the lowest score just for fun. The AI, no way. It's locked into its one single goal. It just can't think that flexibly. So what is going on? What's the real difference here? Why are we so much more efficient, so much more flexible? And it's not just about having a faster brain or more processing power. It's something much more fundamental about the whole approach to learning. And the authors of this paper, they argue it all boils down to one core difference. Today's AI is all about pattern matching. Human intelligence, on the other hand, is about building models. So first up, let's talk pattern recognition. This is what AI is amazing at. It's all about correlation. You show an AI a million pictures of a cat, and it gets incredibly good at finding the statistical patterns of pixels that scream cat. It's super powerful for sure, but it's fundamentally just asking, what is this based on a ton of data it's already seen? But we humans, we do something totally different. We build models of the world. We're trying to figure out the underlying cause and effect. We don't just see a pattern of pixels and say cat. We have a whole model of what a cat is. It's an animal, it has goals, it has physical properties, it behaves in certain ways. We're always asking why. We want to understand how things actually work. So, okay, how are we able to build these complex models so fast? Well, it turns out we don't start from a blank slate. The paper has this great analogy for it. It's like we're born with developmental startup software. It's this core foundational knowledge that's ready to run from a super early age. For starters, we come preloaded with a kind of intuitive physics engine. I mean, even tiny babies get that solid objects don't just pass through each other, and that if you drop something, it's gonna fall. So when we sit down to play Frostbite, we don't need millions of trial and error runs to figure out our character can't walk through a solid block of ice. We just get it, instantly. And the second piece of software we've got is intuitive psychology. We just naturally understand that other beings, people, animals, even little characters on a screen have goals and intentions. So when you watch someone else play Frostbite, you immediately infer that they're trying to jump on the white ice and they're trying to avoid those birds. That lets you learn the game's rules incredibly fast just by watching. The AI, it can't do that. It has no concept of trying. It literally has to die thousands of times to learn that, oh, birds are bad. All right, so once you've got that startup software running, intuitive physics and psychology, we then use these much smarter ways of learning. And it's all about building those rich models, not just finding simple patterns. And to really see this in action, the paper gives another fantastic example. Let's call it the characters challenge. Think about learning a new handwritten letter from a language you've never seen before. The best AIs out there need to see thousands of examples to get it right. But what about you? Well, when you see a new character, even if it's just one time, you don't just memorize the image like a photograph. Your brain immediately starts building a model. You break it down into basic parts, like lines and curves. You figure out how those parts connect to each other, and you essentially create a little mental program, a recipe, for how to draw it. And because you have that recipe, you can not only recognize it again, you can draw it yourself, and you can even imagine what other versions of it might look like. And this all leads to a really key line from the paper. People learn more than how to do pattern recognition. They learn a concept. That's the whole game right there. We're not just creating a classifier, we're grasping a flexible, generative idea that we can use in all sorts of new situations. So what's the engine that powers all this model building? Well, it really comes down to two big ideas. The first is compositionality. That's our ability to build complex things out of simpler parts, right? Like building a word from letters or a character from strokes. And the second is causality, our drive to understand the process that created the thing we're looking at. We don't just see the character. We understand it was made by the motion of a hand. Okay, so what does this all mean for the future of AI? Where do we go from here? Well, the paper doesn't just point out the problem. It actually lays out a pretty clear roadmap for the future. And the path forward isn't about throwing away deep learning. Not at all. It's about making it better, augmenting it. It's about combining that incredible pattern matching ability with more structured, model-based ways of thinking. We need to actually build in some of that startup software, like a basic understanding of physics. We need to design systems that don't just see correlations, but actually learn causal models of the world they're in. And all of this leaves us with one final huge question to think about. If we can actually do this, if we can build AIs that learn by creating these rich causal models of their world, will we finally be on the path to creating a machine that has genuine common sense? Now that is the grand challenge, and you could argue it's the ultimate prize in the quest for true artificial intelligence.